Okay, hi everyone. I'm going to go ahead and go through number 17 from the problems and exercises. This is another great problem that is really, really important to understand. So on this one, they give us a diagram of everything that's going on. And it looks a little bit like this. So we've got our climber here, and she has tension here holding her up with her rope at 31 degrees. And then she is pushing against the wall here. So she's holding herself up with a force, the force in her legs, which is at 15 degrees. And that is it for this part. So we need to find, what does it want us to find? The tension in the rope. Find the tension in the rope and the force that the mountain climber must exert on her feet on the vertical rock face to remain stationary. Okay, so we know that we want the sum of our forces to equal 0. And we know her mass too. She is, okay, so we also have mg pulling down. Okay, so first let's look at the sum of the forces in the x direction. So that's going to be the x component of the legs force and the x component of the tension force. So that's going to be our adjacent for the legs, so the force of the legs times cosine of 15 degrees minus the tension is going to be the opposite component. So it's going to be tension times sine of 31 degrees. And we know that this is going to equal 0, right? Because the net force is in both directions. We have no motion happening in either direction. Next, we have our net force in the y direction. And this one, we actually have 3 pieces. We have our mg, we have the force, the y component from the legs, and the y component from the tension. So these ones, the y component of the legs is going up, the y component of the tension is going up, and the y component of mg is going down. And these are going to be the opposites, right? So this is going to be the force of the legs, not cosine, opposite. So it's going to be the sine of 15 degrees minus the tension times the cosine of 31 degrees plus, so they're going in the same direction, minus mg equals 0. So then this one we can solve for mg really nicely. Sine 15 plus t cosine of 31 degrees. Okay, now we can use this one. We can set these equal to each other so that we can get either the force in the legs or the tension. So we know that F, the force on the legs, cosine of 15 degrees equals tension, right? Just moving that over, times the sine of 31 degrees. So then I can find the force of tension by just dividing both sides by sine of 31. That's not a 3. Of 31 degrees. So I get that tension equals the force on the legs times cosine of 15 degrees divided by sine of 31 degrees. So now I can plug that in here, and I can get that mg equals the force on the legs times sine of 15 degrees plus the force on the legs cosine of 15 degrees times cosine of 31 degrees divided by sine of 31 degrees. Okay. So now we can factor out the force of the legs from both of these so that we can solve because we know this, we know this, we know this, right? So if we factor out the force on the legs, we can actually solve this now. So mg equals force on the legs times sine of 15 degrees plus cosine of 15 degrees times cosine of 31 degrees over sine of 31 degrees. And so then divide both sides by all this chaos. So we get the force on the legs is going to equal mg divided by sine of 15 degrees plus cosine of 15 degrees cosine of 31 degrees over sine of 31 degrees. We can plug everything into our calculators for that. So we've got 52 times 9. Actually, I don't want to do that yet. I'm going to do this bottom part first. So 15, I'm going to start here. Cosine times 31 cosine divided by 31 sine plus 15 sine equals that. Now I'm going to find the inverse of that because it's below and multiply it by my mg. 52 times 9.8. So that gives me that the force on the legs is going to be 273 newtons. And now we know that the tension is the force on the legs times cosine 15 divided by sine of 31. So that gives us that the force of tension is 512. Okay. Now, so that's part A. There's a lot going on there. For part B, we're actually going to look at a different force diagram. So here, instead of looking at the climber, we're going to look at this point where her feet are intersecting with the wall, her legs. So here's the wall, because we're trying to find the force of friction. So her feet are coming in at this angle and pushing on the wall. So we would actually write it over here. Try and get that angle reasonably correct. So the force of the legs. So this is 15 degrees. No. This is what I was trying to draw. 15 degrees here. Sorry. Much smaller angle. So she's pushing on this point with at an angle of 15 degrees with a force of 273 newtons. So this is the force of the legs. And then we know that if she's pushing down, right, because the y component is going down, then we're going to have the force of friction going up to oppose that. And then we have the normal force resisting our motion there. All right, so then we can look at the forces in each direction. So we want everything to equal 0 because we don't want her sliding, right? So some of the forces in the y direction is going to be, let's see, so we have the y component of that is going to be our opposite, so that's going to be the force of the legs. It's going down, so negative force, that's like completely illegible. The force of the legs times sine of 15 degrees plus, so going up, we have the force of friction. Okay, and then in the x direction, we have, once again, opposite direction. So we have the normal force minus the force in the legs times cosine of 15 degrees. And we know this equals 0. We know this equals 0. So now we can find the normal force, which is going to be F in the legs, cosine of 15 degrees. And so then we can find the friction, because we know that friction, we're trying to find static friction here, is mu s times n, right? So now we can just plug in, I'm just going to get us a number for n. So we've got the force in the legs, which is 273 times 15 cosine. So this is going to equal 264 newtons. So then our friction is going to be mu s times 264 newtons. So then we go back up to this, and we can say that mu s times 264 newtons equals the force on the legs. Oh, something cool happened here. I'm going to go back and put this back in because you can't see it if I make this a number. Hang on, sorry. I forgot about that. So mu s times the normal force, which is the force of the legs, times cosine of 15 degrees. So then, this should be Fs, right? Friction static is what that was. So then we can set these equal to each other. So mu s times the force from the legs times cosine of 15 degrees equals this, the force in the legs times sine of 15 degrees. So we end up getting that mu s equals, when we divide both sides by this, our force in the legs cancels, so we just end up with sine of 15 degrees over cosine of 15 degrees. That's why I wanted to get rid of that mu, or that force of the legs that I had calculated out, because I wanted you to see that it actually cancels. So we get 15 sine divided by 15 cosine, which equals the static friction needs to be at least 0.27. So it can be more than that as well. So it's less than or greater than or equal to 0.27 is your static friction on that one. So I hope that that helps with that one. If you did it out to 3 sig figs, sorry, which I should have done because we always do 3 sig figs in physics, you'd get 0.268. Yeah, so I hope that that helps with that one. Thank you.